So for part two, we're going to start at the pharynx and we're going to talk about how food and fluids move through the pharynx, or the lower 2/3 of the pharynx, the oropharynx and the laryngeal pharynx. And then we move into the esophagus, and then we'll move into the stomach, and we'll talk about the chemical and mechanical digestion that happens in the stomach. So the esophagus provides a passageway for food and fluids. We know that this has smooth muscle around it, right? When it's not filled with food, it's actually collapsed. It's kind of hard to show here. There's an image coming up in just a second, but it's kind of flattened. It's not perfectly round. The esophagus pierces the diaphragm at the esophageal hiatus, and then it joins the stomach at the cardiac or cardial orifice. Some people call it the cardiac sphincter. They're starting to change it now to the esophageal sphincter. The esophagus also has a stratified squamous epithelium. If you remember, the esophagus is continuous with the pharynx, which is continuous with the mouth. And so it all has this shared tissue, this abrasion-resistant avascular tissue. It changes to simple columnar when we get to the stomach. And you should remember from 201, columnar is going to be some sort of absorption or secretion, simple meaning one layer, right? So we're going to see a lot of substances being secreted at the stomach. There are esophageal glands that also secrete mucus. Remember, you've chewed up the food, you've dumped some enzymes on it, you've pushed it back to the pharynx. Now it's moving down the esophagus. So this bolus of food has to have something to slide on, right? So a dry esophagus would be bad, be like a dry water slide. So the esophagus has glands that secrete mucus to aid in the movement of food down to the stomach. There are also muscles, right? So at the top part, we have some skeletal muscles, and then as we move down the esophagus, we're going to have more smooth muscle. So this should make sense. We can all initiate swallowing, right? So skeletal, you should be thinking conscious control, right? Voluntary. So we can all swallow, even if we don't have food in our mouth, right? We can tell ourselves to swallow. So the top part of the esophagus is controlled by skeletal muscle, and then the lower part of the esophagus is controlled by smooth muscle. Here's a nice image from the textbook showing you this transverse cut of the esophagus. And this is what we mean by this would all be kind of collapsed. This is still pretty drawn out and open. It would be kind of more flat in the middle here. But you can see the different layers. So this should look very familiar to you, right? We always have a mucosal layer on the inside. Then we're going to have a submucosal layer, which is going to be the connective tissue. Then we're going to have some sort of muscular layer, and you can see the muscles here and here. And then I said, usually we have some sort of adventitia. Last time we saw this was visceral peritoneum. But here we're back to using the term adventitia, which is a fibrous connective tissue. You can look at some of these clinical or homeostatic imbalance items. So one, heartburn. Basically, your stomach is producing a hydrochloric acid, and that can be regurgitated or burped up into the esophagus. So you can also have something called GERD, which is gastroesophageal reflux. So something from your stomach is refluxing or going up into the esophagus. We also have something called a hiatal hernia. This is where part of the stomach is actually sticking through the diaphragm. So remember, it should be esophagus going through the esophageal hiatus, then leading to the stomach. So the stomach doesn't start until after the diaphragm. But sometimes we can have part of the stomach pushed up through that hiatus in the diaphragm. So we get to talk about deglutition a little bit. This is swallowing. So we've already talked about how the tongue and the palate plays a role in this. We also want to talk about the voluntary versus the involuntary part. So the buccal phase, when it's in your mouth, that's the voluntary part because you move it to the pharynx via your tongue. Once it becomes involuntary is once it's in your pharynx leading to your esophagus, it's now controlled by your medulla and your pons. So this is a nice image showing the tongue pushing the bolus of food against the hard and the soft palate. And then by pushing up, it pushes the bolus of food down into the oropharynx and the laryngopharynx. Hopefully your epiglottis closes and blocks off your larynx, and the food is forced to enter the esophagus. So in this first section here, you're controlling this. This is the voluntary. Once you've pushed the food back into the pharynx and the esophagus, now this is under involuntary control. And then we can see we have the peristalsis, or alternating contractions, to move the bolus of food into the stomach. So the stomach is going to be this temporary tank, right? Storage tank that starts the chemical breakdown of proteins. So up until now, we saw the breakdown of carbohydrates with amylase and lipids with lipase. That all started with the saliva in the mouth. Now we get to the stomach and we're going to see proteins are going to start to be broken down, and we'll walk through that process. What's interesting is we change the name now. It's not a bolus of food. It now becomes a paste, and they call it chyme. So basically an empty stomach can hold about 50 milliliters of volume, but it can expand to about 4 liters. So when the stomach is empty, it'll have these folds, these rugae. So basically the rugae are folds of the internal lining of the stomach that can be stretched to accommodate more food if necessary. Here are the labeled sections of the stomach. So here's the esophagus. The esophagus leads through this sphincter here, sometimes called the cardiac sphincter or the esophageal sphincter, right? This area is called the cardia. It's closest to the heart if you're to look at it in the torso model. Then the rounded part is the fundus. We've seen this term before in reproduction when we talked about the uterus. So the rounded top part is the fundus. This area is called the cardia. Everything else is the body. So fundus is just this rounded, fundus is just the rounded section. All of this is body until you get out to here. Now we get to the pyloric region. And then we have a pyloric sphincter that leads to the duodenum. Now this is part of the small intestine. So also they'll sometimes mention the lesser curvature of the stomach and then the greater curvature of the stomach. I also want to mention the greater omentum. So here you can see this is a drape, kind of an apron-like drape of connective tissue and fat, and it sits on top of your small intestines and your large intestines, and it starts here at the attachment point up by the liver. So this is the greater omentum. This acts as a protective structure, a fat storage structure. Think about your small intestines and large intestines are constantly doing segmentation and moving, and this acts kind of as a cushion. There's also this lesser omentum. So you can see here lesser omentum attaches the liver and the stomach. And then they cut away where the drape of the greater omentum would be. So think about if these organs are constantly doing mechanical digestion and they're moving and churning, then we probably want to have some way to anchor them down, right? So for blood supply, in this case, celiac artery, right? Or celiac trunk that comes off the abdominal aorta, we have that gastric artery and those splenic branches, but the gastric is the one that's going to feed the stomach. So if I said, what's the artery that feeds the stomach? You're going to tell me it's the gastric artery. If I asked you where it's coming off the abdominal aorta, it's coming off the celiac trunk. And then remember that the veins from the stomach, the gastric veins, are going to drain back to the hepatic portal and then go into the liver to be cleaned. The stomach has several muscle layers. You can read about it here, but the ones we've talked about already, we've talked about circular muscles and longitudinal muscles when we talked about doing peristalsis and segmentation. But the stomach also has this third layer, and it's an oblique layer. So if you think about it, we now have, north and south, and we have east and west, and then we have these diagonal, right? We have the ability to churn and mix and move the chyme, but you're also kind of pummeling it. The stomach makes me think of kind of a washing machine, right? So you have some sort of agitator and you're pushing the food, knocking it against the side with these muscles, and that is helping to break the food down into even smaller pieces so that the stomach acid, hydrochloric acid in this case and some others that we'll talk about, actually can get inside and start breaking down these pieces into their individual nutrient molecules. The stomach also has a mucosal layer, and that mucosal layer is going to secrete a mucus, makes it kind of alkaline. And this is because the gastric juice, I've mentioned it already, hydrochloric acid, is going to break the food down, but you don't want it to be able to break down the internal lining of the stomach. So you have the stomach producing hydrochloric acid on one hand to break down the food, but then it also has mucosal cells or a mucosal layer that's secreting a mucus to stop that acid from spreading and actually breaking down the entire organ itself. We're going to talk a little bit more about these gastric pits, which lead to gastric glands, which produce gastric juice. And I think the image is a little bit better to look at. Here we have the gastric pit. So these are just lined with surface epithelial cells. And then we start the gastric gland. So if it's a gland, that means it's going to release some sort of product, right? So you can see here in the pink, these are the mucus neck cells. So these are going to make mucus to lubricate kind of this gastric pit, gastric gland, and make sure that the hydrochloric acid released doesn't invade or break down tissue of the stomach. So mucus cells make mucus. That's easy. Parietal cells here, this kind of blue, this is going to make hydrochloric acid and something called intrinsic factor. So we'll talk about the intrinsic factor later, but it makes hydrochloric acid, which helps chemically break down the food that's in your stomach. Then we get down to the bottom of the gastric gland and we have these chief cells. And this is a little bit more complicated, and I do have a slide coming up, but chief cells secrete an inactive enzyme called pepsinogen that gets activated to pepsin, and that's going to help break down proteins. And then here you can see in the green, we have these endocrine cells. So they're inside the gastric gland, and these endocrine cells can actually release substances to either increase or decrease activity of the stomach. Here's an enlarged image so that you can see what these parietal cells are doing, and I tried to color code it for you. So parietal cells are going to make hydrochloric acid, and chief cells are going to make pepsinogen. So this is the inactive form that's released from the chief cell, and then the parietal cell secretes hydrochloric acid. When the hydrochloric acid and the pepsinogen mix, it activates the pepsinogen and turns it into pepsin. And pepsin is what can go and break down proteins and even some lipids. So remember those endocrine cells here? I'm just showing you them up close. We're not going to worry too much about the hormones that are secreted by these, but one of them, gastrin, basically is going to increase digestion. And then another hormone, somatostatin, which can be released by these enteroendocrine cells, can actually decrease stomach activity. And usually that's initiated by sympathetic nervous system. So if you're doing fight or flight, you're going to release the somatostatins, and then that's going to decrease stomach or digestion in the stomach. Here's our summary slide, kind of just what's going on in the stomach. We've been talking about a lot of stuff, right? So there's physical digestion, right? We're doing mechanical, physical digestion. We're breaking down proteins, right? The enzymatic digestion of proteins by pepsin. So remember that pepsin is the active form, where pepsinogen is the inactive form. And how does pepsinogen get activated to pepsin? It happens by hydrochloric acid, right? Which is secreted by parietal cells. All right, great. Here's this intrinsic factor. This is required for the absorption of vitamin B12. And you need vitamin B12 in order to create red blood cells. So if you're missing intrinsic factor, you cannot absorb vitamin B12, and you're going to have a deficiency in red blood cell production. So they call this pernicious anemia. This is something people used to die from before we created synthetic vitamin B12. If something happened and you did not have intrinsic factor and you were not able to absorb vitamin B12, it basically was a death sentence, turn of the century. So remember, we call it chyme now. So it's bolus when it's in the mouth, when it moves to the pharynx, when it moves down the esophagus, when it gets into the stomach, and we've now thrown hydrochloric acid on it, and we've thrown pepsin on it, and we're breaking the food down and pummeling it against the side of the stomach. This chyme is going to be delivered to the small intestine. We can have gastritis, obviously an inflammation from the itis, right? Anything that breaches the stomach's mucosal barrier. So if it gets past the mucosa into the submucosal space, remember we have, that's the connective tissue with the blood supply as well, right? So if we get into that connective tissue and into the bloodstream, we could have hemorrhaging. We could also have the bacteria spreading to the peritoneal cavity. So breaching that mucus wall is not good. And most of the cases where we see this happening is through ulcers. So bacteria H. pylori is one of those that can burrow into and accumulate and make it through the mucosal layer of the stomach and move into that submucosal layer. It's interesting if you want to look it up. We didn't know for a long time that H. pylori was a bacteria that was causing ulcers. We didn't know why people had stomach ulcers, and a team of researchers found that this H. pylori bacterium was the reason, and that once treated with antibiotics, the stomach wall was able to heal, and the ulcers and all of the complications went away. So it's kind of an interesting story there if you want to look it up. Here's our summary slide: digestive process in the stomach. We're breaking down the food, we're holding the food, we're delivering the chyme to the small intestine, we're breaking down proteins by hydrochloric acid and pepsin, right? Any sort of lipid-soluble alcohol or aspirin can be absorbed into the bloodstream here at the stomach, and that the stomach's only function that's really essential to life is the secretion of this intrinsic factor for vitamin B12 absorption. But realize that we have found a way to overcome that, and that we can give you vitamin B12, a synthetic B12 vitamin directly into your bloodstream. What they're saying is, could you survive without your stomach? Yes. Could we give you an IV of all the nutrients that you would need to survive? Yes, we could. Let's walk through this kind of response to the stomach filling. So what happens once the bolus makes it through the esophageal sphincter and it drops into your stomach? What's happening? So one, the stomach is going to stretch. Remember we said we had the rugae in the stomach, the ridges, and it could expand up to about 4 liters. Then we're going to have perisystolic waves, right? So alternating contractions that are moving the food towards the pylorus. And remember, the pyloric region is what leads to the small intestines. So the chyme, here we go. The chyme is either delivered in 3 ml spurts to the duodenum, or it sloshes or is forced backward into the stomach. The chyme enters the duodenum. The carbohydrate-rich chyme is going to move quickly through the small intestine. Fatty chyme is going to remain behind in this duodenum, and you're going to see some of the accessory glands that are coming into play here. So we're going to talk about the gallbladder and how we break down fats a little bit more in one of the next lectures. I think this is a nice image to show you the perisystolic waves, so the alternating contractions. And then here's my pyloric end, and you can see the food, in this case it's the chyme, sloshes out into the duodenum here, and then some of the food, chyme, sloshes back into the stomach. So you constantly have this churning, mixing, throwing digestive, hydrochloric acid and pepsin on the food, and then some of it sloshes out and some of it comes back in, and the process just continues over and over again. Some of the accessory organs, the reason that I'm mentioning them now is because they come into play here at the duodenum. So we have the liver, the gallbladder, and the pancreas. So the liver produces bile. Bile is a fat emulsifier. It breaks fats down into droplets, right? Gallbladder is the storage of bile. It concentrates the bile. So probably the best way to explain this is the liver actually makes the bile, produces the bile, but the gallbladder concentrates the bile and stores it. And then we have the pancreas, which is going to supply more enzymes needed to further break down the chyme. And then we also need to neutralize that stomach acid. Remember, when the chyme is coming out of the stomach, we had been throwing hydrochloric acid on it. Well, now it's going to move through our intestines. We don't want a really acidic chyme. So the pancreas is going to release some bicarbonate, and that's going to help neutralize that hydrochloric acid from the stomach. There are 4 lobes to the liver. There's a right, a left, a caudate, and a quadrate. I'll show you those in the images coming up. And then there's several bile ducts here. We're really only going to focus on the duct that goes from the gallbladder to the duodenum. But there are several ducts. I'll show you those in the image in just a second. So if I said hepatic artery to you, you should be thinking this is coming off of that celiac trunk of the abdominal aorta, and it is oxygenated blood feeding the liver. If I said hepatic vein to you, hepatic vein is once the blood's been cleaned by the liver, it has to get dumped back into the inferior vena cava, and it does that via the hepatic vein. This is why we cannot call the vein that leads to the liver, it's not called the hepatic vein, because we have hepatic veins leading to inferior vena cava. The hepatic portal vein is when we take the deoxygenated blood from the spleen, from the stomach, and from the mesenteric, right, the large and small intestine. So when we take splenic vein, gastric vein, inferior superior mesenteric veins, all drain into hepatic portal. And then hepatic portal goes into the liver, we clean the blood, we go to hepatic vein, and then that leads to inferior vena cava. Here's an image of the liver. You can see the gallbladder kind of peeking out inferiorly from the liver. And you can see the right lobe of the liver is much larger than the left lobe. Here we're looking from the backside, posteriorly. So now we switched it. Here is the left lobe. Here's the right lobe. This little section is called the caudate, and this section is called the quadrate. And again, now you can see the full view of the gallbladder. So remember, all of the liver is filtering your blood. It's also producing something called bile. And then the bile is transferred through this series of ducts into your gallbladder, where you concentrate it and make it stronger. Another image here from your textbook. Here's the liver. Here is the gallbladder. And you can see there's a system of ducts. Here's the cystic duct that leads from the gallbladder to the common hepatic duct. Here's the right and left hepatic ducts. So remember, the liver is making the bile. It gets stored in the gallbladder and then comes out the gallbladder once it's concentrated and travels in this bile duct until we get here to the duodenum. So this is why I wanted to mention this now. You can see that there's a duct from the gallbladder going to the duodenum, the very first section of the small intestine. And then here's the pancreas, and we have a pancreatic duct, and then that also dumps into the duodenum. This is a nice image from back in chapter 19, where we can look at the hepatic portal system again. So remember what I said, the splenic vein, the inferior mesenteric, the superior mesenteric, and the gastric are all going to drain into the liver via the hepatic portal vein. So basically all of your dirty blood, any blood that had contact with bacteria or food that you put in your mouth, we're going to clean it in the liver before we dump it back into inferior vena cava. So these right here are the hepatic veins. And this is something students get confused on a lot. So what's going to the liver? Hepatic portal vein. Liver cleans the blood, and the liver dumps the blood back into the inferior vena cava via the right and left hepatic veins. So think hepatic veins are clean blood, hepatic portal vein is dirty blood. This is another slightly detailed image where you can see the gastric veins, you can see the splenic vein, and then you can see the inferior and the superior mesenteric veins all draining into this section. So basically, if I just drew a box around this section, that is the hepatic portal vein. And then hepatic portal vein leads into the liver. We clean the blood, and then we dump it back into the inferior vena cava via the right and left hepatic veins. Just to make sure we're understanding the branches on the inferior vena cava. So we're draining the legs, right? My mouse is being silly. All right, so we're draining the legs here. Here's our iliac veins, right? Iliac vein is coming up the inferior vena cava. And then we have the renal veins, right? They're draining the kidneys. And then if we come up a little farther here, we have the hepatic veins. We also have the gonadal veins. And they're a little strange because the right gonadal vein goes directly into inferior vena cava. The left gonadal vein goes first to the renal vein and then over to the inferior vena cava. But what I want you to notice, is there any inferior or superior mesenteric vein going directly to inferior vena cava? No. Is there a gastric vein going directly to inferior vena cava? No. Is there a splenic vein going directly to inferior vena cava? No. Why? Because they're all being funneled to hepatic portal. We're doing a real anatomy light version here at the liver. I'm not going to go into great detail of all of the liver cells or hepatocytes. I want you to know the basic functions and then know about the blood flow. So what we just talked about, the hepatic portal and how we're draining the dirty blood into the liver. So we know that the liver is going to do detoxification, right? It's going to clean the blood before we dump it back into the inferior vena cava because that inferior vena cava is going straight to the heart. So we want to try to detoxify as much as possible. We also know that the liver is producing bile. We said the liver makes the bile, the gallbladder concentrates it. And what is bile? It's a fat emulsifier. It's going to break down fats. Remember, your liver can also store glucose. So back when we talked about hormones, right? And we talked about the fact that if you have excess glucose, that you're going to take that glucose and you're going to store it in your cells and you're also going to store it in your liver. And then if you need to release the glucose, you have an immediate supply stored in your liver. Maybe you remember glucagon, glycolysis, right? So go back and look at those terms again. Just make sure you understand that we store glucose in the liver as glycogen. And then we convert amino acids to plasma proteins. So there are proteins that are floating in our plasma that help us maintain that osmotic pressure that we talked about, and that we're going to use some of the amino acids that we have just absorbed, and we're going to use them to build those plasma proteins. We also store fat-soluble vitamins in the liver. Here's a nice image showing you the portal vein. So here's the hepatic portal vein. It's draining all the dirty blood, the spleen, the stomach, and the large and small intestines. And that blood is being funneled through the liver, through these brick-like structures, which are the hepatocytes. In here, you're also going to have tons of macrophages. If we're trying to clean this blood, we want to get rid of any pathogens that might be there, and macrophages are a good way to do that. We also create bile. So these hepatocytes are also creating bile, and we have to have bile ducts so that we can send all of that bile we're creating to the gallbladder to be concentrated. So once the blood comes in, it gets sorted and cleaned through this filter, these hepatocyte filters, and then gets dumped into this central vein. So now it would be the clean blood. We've gone through all these hepatocytes and the macrophages have attacked everything. And now we're clean blood in the central vein, and then we go to hepatic vein, and now we get to dump into the inferior vena cava. Again, we can have inflammation of the liver, right? Any sort of viral infection. If you took too much of a drug that your liver is trying to clean, poisonings, right? You can also have cirrhosis of the liver. So this is chronic inflammation from some sort of infection or alcoholism. Basically, if you turn your liver, if you have those nice hepatocyte cells and they go from healthy cells to fatty fibrous cells, that's obviously going to affect the ability of the liver to detoxify. So basically, if you destroy your liver cells, your hepatocytes, they don't just regrow. And then you'd have to have some sort of liver transplant. But again, it's pretty scarce. It's not like you're just going to get a new liver. And if you have any sort of behaviors, they're not going to put you on the donor list. It's interesting that the liver can regenerate, even if you remove a section of it. But remember, cells are more highly regenerative if we're younger. Also, your liver hasn't grown to its full size yet. So what I'm saying is if I had an 80-year-old, I would not expect their liver to be able to regenerate 80% after removing. We know that the gallbladder stores and concentrates bile. It's going to release that bile via the cystic duct, which is going to flow into the bile duct. So where does that bile duct go? We can see the bile duct here leading to the duodenum. Our last accessory organ here is the pancreas. We know that the pancreas has endocrine function. We've talked about insulin and glucagon before. Now we're going to talk about the exocrine function. So basically, you have cells within the pancreas that are going to secrete pancreatic juice. And then you have cells in the pancreas that are going to secrete digestive enzymes. This image from the textbook, you can see the acinar cells. These are the cells that are secreting pancreatic juice into the pancreatic duct. And then these zymogen granules here are secreting digestive juices or digestive enzymes that are also flowing in this pancreatic duct. So what's coming out of the pancreatic duct and entering the duodenum? Basically, we have an alkaline solution. Remember, we said we have to neutralize the chyme because it just came from the stomach. And the stomach has a pretty high pH because of the hydrochloric acid, about a pH 2. So we have this alkaline pancreatic juice that's going to neutralize the pH of the chyme since it just came from the stomach as it moves through the small intestine. So it's basically something called bicarbonate, and we'll come back and talk about bicarbonate when we talk about acid-base balance. So what are these digestive enzymes? Basically, we're breaking down everything, the last of everything. This is our last chance to break down into small nutrients before we head into the rest of the small intestines to do the majority of absorption. So the digestive enzymes secreted by the pancreas, one, we have proteases. So proteases are going to break down proteins. We have amylases, which are going to break down carbohydrates. We have lipases, which are going to break down lipids. And we have nucleases, which are going to break down nucleotides. So remember that we already started the breakdown of carbohydrates and lipids. We talked about amylases and lipases all the way back when we talked about saliva. So like I said, this is our last chance. Throw some more enzymes on this chyme as it's coming out of the stomach and hope that we can break everything down into the smallest nutrients.